Hi everyone, uh, a warm welcome to this lecture session. So myself Arun and I am from MMO College, Calicut. First of all, I would like to extend my thanks to the HOD of the Electronics Department, St. Thomas College, Thrissur, as well as Mrs. Ridhushri, with whom I used to have contact for the past couple of weeks to come up in front of you like this. She took really very good effort to arrange a lecture session or coordinate me to put me like this in front of you like this in behind a light board and give you a session on a very specific topic, very relevant topic. Okay, so the title of the topic is instrument and electronics, a perfect sync, in a perfect sync. So that's how I used to put it. If you call why I am taking this topic, because it's been a very old topic. It's been a very old combination, a very successive combination. This instrumentation and electronics. Instrumentation and electronics. So why I am taking this topic back again to present in front of you is because my background is in electronics. I did my post graduation in electronics, and for the past 7 years I am dealing with instruments. My PhD is on instrumentation. So I could find a perfect synchronization between these two titles, like electronics and instrumentation. So this is how I thought, okay, let me come up with some different idea to emphasize the influence of electronics in instrumentation. Okay, when you talk about instrumentation, a small safety pin is an instrument. You know that, okay? A small safety pin, say for example, you take a safety pin, it is for a use, for specific use. So you call that an instrument for a specific use. Likewise, you take this pen or you take this tool, a light board, or you take for granted anything that you come across in your life, day-to-day life, is an instrument. So an instrument, if you define an instrument is something that serves a specific purpose. And uh, earlier times, instruments used to work as a standalone system, where it works for a specific system and it collects data and give you data in many forms. Okay. Then by the emergence of electronics, I am talking about very hi-fi electronics. By the emergence of electronics, instrumentation, the scenario of instrumentation changed entirely. So this is the point where I used to emphasize the instrumentation field got a very good backbone with the support of electronics. So that's how we used to put it. That's how I would like to put it, this lecture in towards that direction, because we know that this combination is there in our engineering stream, in our graduation stream, everywhere. So the newness of this thing is I would like to take you to a few couple of examples and to show how electronics really complements instrument for its very high better usability. So that's how I used to put it. Okay, so before going into the core of this title, I would like to show a small example here. Uh, See, out in here, you can see in this animated picture, the source you can see from here is being splitted in two directions, and it's been modulated. And this modulation is the capability of that instrument. So this is actually a scattering experiment by particles inside a soluble, inside a solution. Okay, and the detector, which you can see from this side, the detector here. So this detector is been switched efficiently. So it's an indication, but it's been switched efficiently to pick up the specific light from these two sources, where it is getting splitted in the input section. So this is a very perfect example of automation of an instrument. So the instrument is as such there for years and years long back, but when you couple it with electronics, the dimension of the instrument changes. it's become more usable. The usability of the instrument really increases a lot when you couple electronics with the instrument. So this is how it's done. And before going into the technical side, I would like to walk you through a small example, one more example in this direction. That is, say, you might have seen this picture. So this is a jar, and you can see two frogs sitting in two sides of this jar. There are two dragons. So from this you might have got a clue. This is a cross section of that instrument. Yes, of course. So this is an instrument that is used for monitoring earthquake in older times. Actually invented by the ancient Chinese people. So it's a very, this was the first instrument, you can say, if you check the history of seismometers. So the focus is on seismometers. So this is my first example. So if you date back, if you check the history of seismometer, so you can see that this is the first ever invented seismo detector. You can say seismo, instead of seismometer, you can say seismo detector, first ever built by the Chinese people. Okay, so the working principle is very fantastic here. You can see a heavy mass suspended inside the jar. So due to inertia, this heavy mass will tend to move in opposite direction of the ground. Okay, so if the ground is moving forward, so this inertia tends to keep its position stable. In that way, it causes its position to change. So that this bar is attached with an axial system which is connected to the dragon's mouth, and there is a ball, there is a metal ball inside the mouth of the dragon, and there are like 8 frogs around the jar. So it's a cross section of this instrument, 8 frogs around the jar and 8 dragons with the ball inside the mouth. So you can actually pinpoint by seeing which ball is falling into the mouth of the frog, and you can actually pinpoint in which direction the earthquake came. So that's how they made such a fantastic instrument in the beginning to monitor the seismic events. Okay, so this actually evolved and it went on to the analog system. So the instrument got evolved, and this everyone knows. This is a seismograph, where you can see a drum carrying a paper with a stylus, and the stylus is again connected with an inertial mass. The principle is same. So when any change in the mass will cause the stylus to move, and this will be recorded on the paper. So this is an analog kind of instrument, which is a very old technique. The problem with this instrument works really well. Okay, the problem with the instrument is it is not very sensitive. It cannot sense very feeble vibrations. Okay, then came the real magic. So this is a current modern version of the seismograph. What you are seeing on my this side is the perfect in combination of all the things in a small box. It is digitized, it can store, it is connected to the cloud, it is connected to the IoT internet, internet via IoT systems, and wherever you are sitting in the world, you can access the data from this instrument, and this instrument is very stable and very sensitive. Okay, so right from this, so what I want to emphasize is the principle of working of this instrument. Even you take this analog, even you take this digital, is same. Okay, so but you can feel the difference, right? Here a ball is used to detect the seismic events, but you come all the way to this part, everything is digitized. Even a small feeble movement of a truck passing by is monitored in this instrument. So what is actually increased? The sensitivity of the digital system has been improvised a lot. So coming to the features of the combination. So these two combinations, if you take the features from this example, so there are many plus points of attaching electronics or combining electronics with instruments. Okay, the first thing, as I mentioned, the sensitivity of the instrument could be improved a lot. Okay, so what do you mean by sensitivity? Even as I mentioned, a small truck passing by, near to that instrument, this instrument could sense. Okay, the reachability of the instrument is also improved, okay, that a far away event could be monitored using this kind of instrument. The selectivity is also improved by incorporating electronics, a huge amount of hi-fi electronics into instrumentation, okay. That is, you can actually select the variable which you are interested in. So that's what I meant as selectivity. You can pinpoint the variable which you want to measure, okay. Then it is very easy to analyze the data and store the data later for the later purpose, if it is digitized. You all know that. You might have dealt with DSP, digital signal processing, where you have a set of data which is like analyzed in real time scenario. So that's the advancement of electronics that's happened in the past few years, that you process the data then and there, give an output, and so that you can interfere with the instrument to correct it. So that's the amount of precision and capability the instrument got because of the backing of electronics, okay. And it helps to automate and control. See, as I mentioned, this small box is very easy to control, it is very easy to carry, it is highly mobile, as you can see from small box, okay, and it is very easy to automate the entire setup. Say for example, if you are carrying the instrument, the inertial mass should not move so that the instrument is not getting damaged. So such kind of things could be automated, okay. So the automation part varies from instrument to instrument, the controlling variables varies from instrument to instrument. So this all can be done with the help of electronic boards, okay. Then as I mentioned, with the emergence of IoTs and cloud computing, you sit in the other part of the globe, you can get access to the data which is been recorded in the instrument, because this instrument is a part of IoT system, is a part of the network. So wherever you sit, you can actually track the instrument or exactly monitor what happened in so and so date, so and so hour, so and so second, even to the microsecond level. You can track the event even if you are sitting in a different part of the world, okay. One main important part I would like to mention is SNR, that is signal to noise ratio. Yes, so signal to noise ratio is a very important aspect when you consider instrumentation, because an instrument basically works on the basis of differentiating the signal from noise, okay. So if this is poor, then yeah, you are getting garbage from the instrument. So with the proper incorporation of electronics with the specific instrument, you can actually improve the signal to noise ratio a lot. So that's why I would like to emphasize on this part. So the signal to noise ratio of the instrument really improves a lot with this combination. So perfect electronics combined with the instrument could actually improve your data, as well as improve the usability of your data, okay. So let me move on to the technical side of this discussion. Okay, so I gave you a very small clue of how an electronics could be incorporated with the instrument to improve its usability and working capability. Okay, so considering these facts, I have two examples to discuss in front of you. So one is a very popular circuit which is been used with all instruments which works on the basis of optics, okay. Optics. So any instrument that uses optics as a source and a detector on the other end to sense that optical signal which contains very valuable information. So in that sort of instrument, this circuit is very important. So the discussion point is lock-in amplifier. Lock-in amplifier or detector. Lock-in amplifier or detector. So a lock-in amplifier actually consists of a lock-in section, where it basically, if you represent in block diagrammatic representation like working of the lock-in amplifier. So you have the signal Vs of t, okay, which is like this. Imagine this is a signal which is submerged in a very noisy environment. Okay, so this is Vs. Imagine this is Vs. Okay, now you have a reference signal Vr of t, so which is having a specific frequency like this. Okay, so you feed these two signals into lock-in amplifier, and what you are getting in the output is only this signal. So you are getting the output here. So only this signal which you want to see minus the noise. Okay, so what is actually happening here is a lock-in amplifier. If you want to define a lock-in amplifier is a device that actually get rid of all the noise component. If it is a very noise environment, it will just take the signal alone and give it back to you. So now you might know, you might understood like why I mentioned optical instrumentation, because optics interfere with lot of noise. Like for example, ambient light is a noise, and you cannot. It is very hard to get rid of ambient noise. Okay, from the instrument. So you can use a lock-in amplifier circuit in order to basically get rid of all the noise, or if you want to see only the frequency or only the phase or the amplitude differences in the wavelength that you are interested in, you can use a lock-in amplifier. So that's the use of lock-in amplifier. It actually is a filter. It's a very perfect filter where you get rid of all noise components and just have the desired output that you want to see. Okay, so moving into the the real part of lock-in amplifier, as you can see from here. Let me just get rid of this part. Okay, so a lock-in amplifier, as I mentioned, is shown in this figure here on my right. So it's a representation of a lock-in amplifier used in conjunction with a chopper. I will explain why this chopper is used for, and it's for detecting some absorption event. Okay, some absorption in some material, some soluble. Okay, so you have a laser, then a chopper, and then the entire system. Just forget about this system, and then you have this lock-in block, and then the reference signal. Okay, so what's happening here is you actually you know what laser is, right? It's a monochromatic, highly beamed or omnidirectional light source, and it's actually a coherent kind of beam. Means it consists of only one wavelength. So this laser will lace at a particular frequency. If it is continuous, it will be interfered with the ambient light. So what we want to do is we just want to make the laser pulsating. So instead of a continuous lacing action, what we will do is we will make it into pulsating form of thing. So that's why you use a chopper. So this is a fan actually. Use this chopper for this purpose. So this now you know the frequency of this, because you know the frequency of the chopper. Okay, so you just chop the laser like that and use the same frequency. You just send it through the system. So this is the system. Okay, where you can see a an arrangement here. Okay, to absorb or scatter or something which you don't have to worry about. Then you will get an output from the system. So this is an output. Okay, so this output is fed to the, now this is fed to the lock-in amplifier. So this output is fed to the lock-in amplifier. Then you have the reference of the chopper also fed to the lock-in amplifier. So there will be a mathematical process happening inside the lock-in amplifier. But this lock-in amplifier itself is a circuit, electronic circuit, and what you get is you will see only the amplitude shift in the laser. So what I mean is, for example, suppose this is the output. So let me just hide this one. Okay, so this is the laser amplitude shift, and this is time. Say this is a laser amplitude shift like this, and this is actually submerged in like high heavy noise if this uh, you know lock-in amplifier is not used. Okay, so what actually happens here is the phase of this reference signal and the phase of this output signals is actually matched. So this is how it is done. So it will take only those signal with those phase match. Okay, so that the uh, change in amplitude of this laser signal is exactly retrieved in the output of this lock-in amplifier. Hope you got what I said. Clear? So the phase of this lasing thing and the reference is matched, and only those part is taken out and plotted. Only thing is you will get a pulsated output. It's okay if you just do a quick sampling, or if you just digitize it and do a quick processing, you will get a continuous signal as before. Okay. So this pulsating, actually you can actually fix this pulsating, and you can say what resolution you need to make it retrieved in the output, or the desired resolution that you can design, okay, earlier. So this is how the lock-in process works. So it actually matches the phase of the pulsed source and the reference from the same pulsed source out of the system, and then mixed in the lock-in amplifier and retrieve the output in the desired way. So it actually get rid of, so the system consists of lot of other lights, okay, and output consists of heavy noise. Okay, so this is what I said. So this output consists of heavy noise, and this lock-in will fix that phase, okay, this phase to the phase of this output, because output will also consist of what? Signal, right? So that signal is been like filtered out. That signal is been matched with the reference to take only the signal out from a pool of noise. So that's what I meant. So then finally you can retrieve the signal like this. So very good electronic circuitry example in in combination with instrument. Like majority of the optical based instrument use lock-in amplifier, so that they get a very perfect output. In fact, we did an experiment a couple of years back in China, where we have to transmit laser to a long distance. Okay, and in the outdoor environment, and the outdoor environment is full of noise, like ambient light anywhere from the street lamps, anywhere like that. So we used a lock-in amplifier to get only the laser wavelength that we thought of, okay, or that we designed. So not only this application, any application that use optics as a source and an optical detector use a lock-in amplifier in the as a very perfect filter to filter out only the signal. So that's why I told you the signal to noise ratio is an important factor. So this signal to noise ratio is been improved a lot and lot and lot. So before earlier, if this is not used, you cannot actually differentiate the original shift in the amplitude of the laser due to the system. Okay, system imparts some shift in the amplitude. That's what we want to see actually. So we cannot see before the invent of lock-in in 1930. We cannot see we cannot retrieve the output signal from a system. So now it is possible with the help of lock-in amplifier. So thanks to R&D in this area of electronics, because of which many optical based spectroscopic instruments have been built. I mean, especially in the ambient atmosphere. Okay, hope you got the the hint of why we want to combine electronics with instrumentation. Okay, so now we go into the real electronics part of this lock-in amplifier. I will just skim through it. Okay, so this is the circuitry of lock-in amplifier. So don't get tensed by seeing the circuit. So it's actually very simple if you look from the splitted angle. Okay, so this part, so right vertically, so this part is a amplifier system to amplify the weak signal, and this is the demodulator system, lock-in demodulator system, and this is the low pass system. So right in the third section. So you have actually three sections. One is amplifier section, then the the demodulating section, that is lock-in demodulation section, and then the low pass filtering section. So this low pass filtering section is very important because it actually takes only the signal. Say for example, this the nature of the noise. The noise is having very high frequency. So that this entire system is a filter, lock-in is a filter, but this low pass filter plays a very important role. You have to actually fix the cut-in frequency where you are looking at. Okay, so this depends upon the resolution of the pulse that are you given to the source. Okay, I mean the chopper frequency. That's what I meant. So you want to really design this low pass frequency with a bit care of the chopping frequency. Okay. So now again this chopper is not being used. Nowadays we are using a modulated signal to the laser, and this laser has been turned on and off in a particular frequency. So no mechanical element there as chopper. So this is the actual circuitry of lock-in amplifier. Okay. Testing of lock-in amplifier takes real pain. Actually, this is the first assignment that I got when I joined as a research scholar here in NIT Calicut. so this is the first assignment I got from here, and I got it through. Like this instrument, an instrument in Ireland is still using this board which we made for lock-in purpose. Okay. So there is another version of lock-in amplifier. So this is a digital version of lock-in amplifier. So where you have say digital version, if I say digital version, then you should have to think about the digital signal processing. Okay, so you should think about the signal. So I would just give a quick reference of what I am saying. Actually, the lock-in is a mixer of what? As I mentioned in the symbolic diagram of locking, it's a mixer of the signal which is having pulse in nature with the reference signal. Okay, so it is actually getting mixed up. So you can say it is mixed up, and a process is happening there which is like a sensitive phase detection system. Okay, the phase of these two signals will be matched, and it will take only those signal with those phase matching. Okay, so you can say it's a phase sensitive detector happening inside the lock-in box. So that's a crucial process that's happening inside the lock-in amplifier, that is phase sensitive detection. Okay, so if you write it in mathematics, like V phase sensitive detector is given as the input signal, the reference signal VL sine omega RT, sorry, this is actually R, okay, sine omega RT plus theta signal. So this is the phase multiplied with sine omega LT plus theta signal. So this is the let me correct it. It is actually VL, sorry for my confusion. So this is what is happening inside a lock-in detector. Okay, so these two signals, so V signal is the amplitude, this is the frequency, and this is the phase. Okay, this is the frequency of the reference, and this is the phase of the reference, sorry, frequency of the signal. Okay, so it's actually getting multiplied. The process which is happening inside the lock-in is this. You are multiplying these two signals, right, as I mentioned before. Once you do this, I am not going into the further mathematics, you will get two AC components. Then you use as I mentioned, you use a low pass filter to get rid of these two AC components. What left behind is perfect DC points that you can plot on the basis of time axis. Okay, so this is what you want in finally in your lock-in section. This is time, and you have to actually get what's happening with the help of the system. So this is what you want to see. So this could be achieved with the help of this digitizing the process. So this is where we use digital signal processing to implement VPST or this equation. Okay, and low pass filter, the PG students of electronics might know or might know to design using digital signal processing kits low pass filter. So low pass filter very easy to implement using various algorithms. You might have came across these algorithms in your laboratory. Okay. So, this is how this box here on my right has been built using I mean incorporating this algorithm. So, this is how you can digitize the lock-in process. Okay. So, this is one example of using a perfect electronics board like a lock-in amplifier or lock-in detector board with any optical system, as I mentioned, with the help of chopper, the lacing arrangement that I mentioned before. So, any sort of instrument could use this locking amplifier to take out the signal alone from the pool of noise. Okay. So, the second instrument I would like to, or second example I would like to discuss with you is, I'll take FTIR. You might have know what FTIR is. It's like Fourier transform infrared spectroscopy. Okay. So, FTIR is a very popular tool used to detect the molecules, or to conduct the molecular spectroscopy to identify which kind of molecule is present in so and so compound. Okay. So, it actually works in this principle. An incoherent like multiple wavelength beam is being hit on that molecule, and the molecule will absorb or scatter depending upon its atomic energy, and this instrument will look at the infrared region of that absorption or scattering process. So, that is the principle of FTIR working. So, this is the brain or the core of FTIR system. So, it is an arrangement of the core principle of working of this FTIR is Michelson's interferometry. Okay. So, Michelson's interferometry is used for many purposes, and this is one of the purpose of its usage. It has a source, it has a detector, then it has two mirrors, one stationary and on this end movable mirror. Okay. So, this I won't go very deep into Michelson's interferometry because the focus is not there. Okay. So, this mirror will just understand that light passes in these two axes, like light from the source, it just goes all the way to mirror 1 and then to the moving mirror. It comes back and gets absorbed in the detector. Now, this will have all the information regarding the response of the sample. Sample will be kept anywhere in the path. Okay, response from the sample in each and every wavelength. And how do you simulate wavelength using this experiment? See, this movable mirror arrangement will cause the wavelength to shift. So, that is the core of the working. So, just understand the principle, that is all. Okay. I am not going into very deep of this instrumental concept. So, this movable mirror will cause the wavelength to shift. Okay. So, that you will get by moving the mirror from one point to another, you can actually record the entire spectrum, okay, the response of the molecule in the entire spectrum. So, that is how FTIR works. Okay. So, our focus is how to move the mirror so that each and every point of that mirror position corresponds to its wavelength. So, for that we use a system like this. So, this is a solenoid kind of arrangement which I took from the infrared FTIR spectrometer. Okay. So, this is a coil arrangement with a magnet inside this dome and with a mirror attached to the system. You can see this is kind of a tube, right. So, this tube alone won't make the mirror to move. You need to attach something along with this. So, that is the coil. So, this is very specific purposed coil which will be connected to the solenoid of this arrangement, so that the current is very precisely adjusted, so that mirror will take each and every position which depends upon the designer, okay, which position corresponds to what wavelength. So, that is the core of FTIR. So, this mirror movement has been adjusted with the help of the current flowing through the coil. Hope you understood the point. And this current has to be controlled precisely, so that this current corresponds to the wavelength in the output. Okay, each and every position of the mirror is being controlled by the current, and so that the current corresponds to wavelength that you are seeing the output. I hope you got the connection. Okay, for that you need a very precise circuitry to control this current flow in the coil. So that's the if you get a chance to open an FTIR, you can see a very complex board behind the instrument. The instrument as such is very simple. As you can see, a detector, a source, two mirrors. That's it, and follows a Michelson's interferometric principle. But behind the scene is the electronics working out. Clear? So that's what I want to see. Each and every millimetric movement has been controlled precisely by the current flowing through the coil. So that's how this mirror attached to the magnet is getting moved. Then you will get a shift in wavelength, and this has been recorded in the output. Not only that, this current has to be synced with the wavelength that you are seeing in the display of the instrument. Okay, for that you need very precise instrumentation or very precise board to interact with the current flowing in the coil with the wavelength that you are seeing in the output. So that's the amount of electronics that's been used in today's instrument, so that you get a much better and better output from the instrument. Okay, so this is the couple of instruments that I would like to discuss at this moment, just to demonstrate how electronics has really helped the instrument to move a huge way. Clear? One small example of my own research. I'll just wind up with this small example. So let's get rid of this thing. So my area is like it's known as, it's again spectroscopy. Okay, and a spectroscopy, as I mentioned, a spectroscopic instrument will detect the species which is present in the sampling chamber. Okay, whether it might be a liquid or it might be a gas or it might be a solid. Okay, so my area of research is to monitor the the pollutants present in the atmosphere, both gas as well as aerosols. Aerosols are small tiny particles suspended in the atmosphere. Okay, so for detecting the gas, we have devised an instrument known as CEAS, which consists of very highly reflecting mirrors. So you say this mirror 1, mirror 2. So which is having a concave form of nature in one side. So you just face these concave faces of these two mirrors face to face. So there will be a source at one end, and there will be a detector. So this is a simplified form of this instrument. Okay, so source will send light. The source could be a laser or a broadband consisting of many wavelength. So the light will pass through the mirror 1, and then mirror 1, both the mirrors are partially transmitting. So light will pass through the mirror, and it will hit on this face. Since it is highly reflecting, it will be reflected back. Since it is concave, you can literally have n number of reflections, and each reflection there will be some component coming out, because as I mentioned, it's a semi-transparent mirrors. So this small component will have the information. So this has been detected by the detector here. So this is the very crude form of explaining CEAS, cavity enhanced absorption spectroscopy. Okay, where you can really study the light extinction caused by different species of gases. So that's the main use of this instrument. And if you use a broadband, for example, I'll just say nitrogen dioxide will have a very strong absorption at 400 to 410 nanometer. Okay, nitrate NO3, which has a very strong absorption at around 632 nanometer in the red region. Okay, iodine, a very important trace pollutant seen in the polar regions, has got so iodine, a very common pollutant seen in the polar region, has the absorption around 532 nanometer in this region. So you can see each wavelength band has got each species has got its own signature and different wavelength bands. So that's what I meant. So if you are using a very broadband source, okay, very broadband source, say a very powerful bright light, you can actually detect all the species using a single instrument. Okay, now my focus is on the source. The source is a very expensive instrument at the moment. We are using very expensive instrument as source because it should be really powerful. It should be having a provision to collimate the light inside this tunnel or the sampling chamber. So there was an idea proposed by me some couple of years back to use the source. So instead of using a source as such, use sun as the source, using sun as the source. So for that I actually improvised the instrument. I actually improvised the instrument like this. So this is a sampling chamber, two mirrors will come here, okay, and it is looking at the sun, and it is actually using a lens. You can tunnel the light inside, then you use some detector for that, and then you use the computer. Detector is connected to the computer to get the anyway this part is not to be mentioned at the moment. So this instrument actually tracks the sun. For that I actually instead of using a light sensor, I used a zenith angle of the earth has been considered, and this instrument will follow that zenith angle on every time average, okay, so that it can track the sun precisely. Okay, so here the electronics part comes in this point because the precise electronics, that's what I meant, okay, because sun is often hindered by clouds or any form of dust or anything like that, or heavy particles like smoke kind of thing. So this light source is not very stable. So you need to normalize those effects in the instrumental output. So what do you mean by normalize? You just get rid of those effects in the output, right? So for that I actually proposed two detectors. So you can say D2. So D2 attached very near to D1, and D2 will look at the sun very near to this arrangement directly without the chamber, so that you will get a proportion of the light coming from the sun here, and then you normalize with the output that you are getting from the system. So just like I mentioned in the lock-in, something similar to that is what I designed for this instrument. So these two detectors has to work in a synchronized fashion, then it has to normalize, it has to actually do, there's a bit of FTIR or sorry FIR filtering and normalizing process which is happening in the background using electronic systems. So then this entire system was automized. So what I want to emphasize is that my experience in electronics really helped me a lot to improvise the instrument that is being currently used even today, without having any electronic support. So there are lot many instruments in R&D as well as in the commercial field where they need to be used in a much better way, where electronics can really go deep in to help those instruments to work in a much better way. So that's what my point is. So that's how I would like to conclude that by by incorporating the knowledge of electronics into even the current form of instruments, you can actually improve the capability of the instrument a lot. Instrument alone will have certain amount of capability, but if you add electronics, you can even improve the capability of instrument to something like 10% capability of the instrument. So that's what my point is. So electronics works everywhere, okay. As far as I'm concerned, I'm very lucky to work in these two areas like instrumentation and electronics, and also I am lucky enough to combine these two fields in a much better way for the betterment of scientific world. So thank you very much for listening to me. If you have any doubts, just throw back to me. I would like to help you in the limited knowledge span that I have. And once again, I would like to thank for giving me a chance to present my little bit of experience in front of you. So thank you and have a very nice day. Bye.